Kia ora, everybody. We are going to get started now. E ngā iwi, e ngā mana, e ngā hoa mahi, tēnā koutou katoa. E mihi ana ki a koto, kua tai mai ki te tautoko tēnei kaupapa. Ngā mihi nui ki a Dr. Belinda Storey, te kai kōrero o te rā, tēnā koe. Ko Vicky Plater tōku ingoa, nau mai, haere mai ki te tai wahanga. Kia ora, everyone. Welcome. It is wonderful to see many of you online today for our Treasury guest lecture. And it's a pleasure to have Dr. Belinda Storey as our presenter this morning. This is part of our theme for the current Treasury guest lecture series of fiscal policy for the future. And this explores the role of stabilising, sustainable and effective fiscal policy. We chose this theme as resilient and sustainable fiscal policy is essential to the living standards of all New Zealanders. Our guest speakers have been providing us with insights into how fiscal policy can support government to meet its current and future obligations, while adapting to changing circumstances and delivering value for the New Zealand public. So today, I'd like to introduce Dr. Belinda Storey. Belinda is a Managing Director of Climate Sigma, an independent research organisation where she developed the climate leases model for valuing property under climate change. Back in 2017, she introduced the term insurance retreat, a concept that has shaped national and international conversations on physical climate risk. Her research focuses on the impact of physical climate risk on infrastructure, banking, real estate and insurance. Belinda has also been Director of the SOE Assure Quality, is a member of the Independent Reference Group for the Ministry for the Environment's Adaptation Framework. And in 2022 was named Wellingtonian of the Year for Science and Technology in recognition of this work around pricing physical climate risk. So, coming to the substantive topic, which I personally am very interested in and looking forward to Belinda's presentation. We all know that climate change is increasing the frequency and severity of extreme weather events, raising important questions about how we prepare for the future. The Treasury has long recognised the important implications climate change will have for living standards, including through economic and fiscal channels. So understanding climate change and its potential impacts is a really important part of considering stabilising, sustainable and effective fiscal policy. So today, Belinda will talk us through how these developments can affect investment decisions and the availability of insurance for residential property, and discuss how infrastructure planning and budgeting can better account for the long-term impacts of climate change and the potential fiscal liability for the Crown if private insurers retreat. Just in terms of logistics, before I pass to Belinda, we will be using the Q&A function on Teams, so please post your questions there. If you have any technical queries, just use the standard chat function and the team will try to resolve that. And now I have great pleasure in passing over to Belinda. Thank you, Belinda. Welcome.
Kia ora koutou. Thanks for having me. I'm now going to share my slides. Today I'm going to be talking in three parts. I'm going to be talking about, give you some general context about the rate of change in climate change. I'm then going to be talking about a concept for valuing the loss of value in infrastructure under climate change. And then I'm going to talk about the potential liability for the Crown if public insurance was to be extended when private insurers were to retreat. So there's going to be three sections of the talk today, and I'll just kick off with giving you some context around the pace of change that we can expect to see in the next few decades. So just get that started. Oh, sorry. There we go. So to begin with, when we're thinking about climate hazards, I'm going to talk about three. Oh, sorry. Here we go. So 3 climate hazards. I'm going to talk about climate hazards. First of all, when you see any sort of news from internationally about climate change, you're likely to see information about temperature. Temperatures are changing the fastest as terms of a hazard, and that's partly why you'll see when they talk about attribution science, where they're talking about the impact of climate change and how much you're able to determine a particular event being attributable to climate change, they're most confident about heat waves, and that's because there is a significant shift in those distributions. I'm going to talk in the next slide about what that means in the context of Aotearoa, because while the temperature is changing, the impact for Aotearoa in the near term is limited, and that's largely because of our exposure to that at the moment. The next hazard within Aotearoa that's changing is in terms of wildfire. We have relatively low exposure, but it is changing. Then the next fastest changing hazard is coastal, and that is largely because of, not because sea level rise is changing any faster around Aotearoa than others, but it's just that our relative circumstances and with regard to the size of storms means that a very small amount of sea level rise causes this very significant change in the hazard for us. And then the last one is the rate of change in inland flooding is much more, is slower, but we have far more assets exposed to inland flooding. So just to give you some context about it, the amount of exposure that we have in terms of temperature is very low. That's largely because we live in a mid-latitudes with a temperate climate. In fact, temperature has been so little of an issue for our country. In the past, the only measure that was related to health that was related to temperature was a standard was established for cows. So we haven't previously had a measure that is measuring the potential impact of heat waves on individuals. Now, work by a colleague of ours, Luke Harrington, has worked with Met Service to introduce a new standard to enable Met Service to provide that sort of warning. So they're similar to what we have as a UV index. We are putting in measures place to help provide that sort of forewarning, but at the moment the hazard is relatively modest, even if it's changing fast. The next one is the rate of change in wildfire. So that's work that's been done again by colleagues Nathaniel Melia, is looking at how the rate of change in wildfires is significant, but we don't have a lot of assets that are in wildfire zones at the moment. So again, the exposure is relatively modest. And then thinking about coastal change, the hazard is changing significantly, but the exposure is relatively modest in the sense that for every one house at the coast that we have exposed to coastal inundation, we have 10 houses in inland flooding. So the rate of change in inland flooding is lower, but we have far more assets exposed. I'm going to be talking about these terms, so I'm just going to give people who aren't familiar with this concept a very quick refresher. So disaster risk is a combination of hazard times exposure times vulnerability. If you're thinking about water, what that means is hazard is how much water is falling out of the sky and whether it's the hydrology delivers it to your location. Exposure means is whether the water actually reaches your asset or you as an individual. And vulnerability means that if that water reaches you or your asset, how much damage does it cause? Vulnerability can also mean financial vulnerability. So, for example, insurance doesn't reduce risk, it transfers risk. It doesn't reduce the hazard, it doesn't reduce the exposure, but it can reduce the financial vulnerability so that if the water turns up, it causes you less financial distress. So that's just giving you a refresher because I'll be using those terms throughout the talk today. Now, to give you some context about these rates of change, because I'm going to be talking about rates of change throughout this discussion, I wanted to give you a little bit of context about where we are in terms of global temperature change. And what I've done is produced here an illustrative example. It is illustrative. If there's any climate scientists on the call today, I'm sure you'll tell me that there's some nuances about the particular standard deviations. But generally speaking, we are approximately 1 degree warmer than pre-industrial. And so the baseline that is used in climate modelling is 1850. And what you'll see is that there was a modest rate of change for the first 120 years. So for the first 120 years, approximately, there was an increase of about 0.5 degree. And this distribution is indicating that we've got approximately half a degree of warming equates to about 1 standard deviation, which is approximately what you would see in the UK or New Zealand in a temperate mid-latitude location. So we had about half a degree warming in the first 120 years, and then we had another half a degree in the next 50 years. So the first 1 degree took 170 years to eventuate. We're now going to be having another 1 degree in the next 30 years. So the rate of change is very significant. Now, there wasn't any magic number about 2020. I just wanted to be able to provide the comparison. The curve doesn't suddenly get steeper in 2020. It's just that that's the approximate rate of change average over the previous 50 years compared to the next 30 years. Now, the distributions are shifting to the right, but they're also changing in shape. So just to recap, you've got about 170 years and then 50 years. So they're changing in shape, which means the curves are getting flatter. When you're thinking about COVID, flattening the curve was a really good thing. When you're thinking about climate change, flattening the curve is not a good thing because it's a symbol that the natural system is unstable. The natural system will revert to its normal distribution, or it's in the case of other distributions that we work with, it will once the global system reaches equilibrium, once there is an end to the emissions, whenever that may be, you will have it return to its normal state. So what does that mean for the change in probabilities of extreme events? So if you look at the bottom, the black corner in the bottom, excuse me, that is a 1 in 100 year probability event. So as that distribution shifts, obviously there is a very significant increase in the probability of those events. For those of you who are wondering where we will get to with a 2.7, sorry, we will get to with the nationally determined contributions. So the nationally determined contributions, if every country in the world was to meet the commitments that they've made under the Paris Agreement, then you would be looking at 2.7 degrees. So that's the approximate estimation of if all of the commitments that have already been announced were to be met, then you'd be looking at 2.7. So that's an overview of the rate of change in climate globally. And now I'm going to be talking about how you might translate a rate of change in extreme events when thinking about infrastructure. So I'm just going to give a little bit of a chat here about the key number that I work with, which is the design life of infrastructure. So I'm just going to give a little bit of a background around that, and then I'll talk through some of our findings with one case study. So when I'm talking about these, there's going to be a bunch of definitions, so let me just throw some of those out. So an average recurrence interval, or ARI, that is what you will see when you see something saying it's a 1 in 100 year event. What that is saying is what's the average period of time between an event of that size. So if you have you might have a 1 in 100 ARI or a 1 in 5 ARI. That's an average recurrence interval. An annual exceedance probability is a counterpart to the ARI, and for low probability events, so events that are 1 in 100 or bigger, then you can simply flip it upside down as a fraction. So, for example, a 1 in 100 year ARI works out to be a 1% AEP. And an annual exceedance probability is just what is the probability of that size event occurring per year. A probability of exceedance allows you to extend that time period. So you're not just looking at a 1 year, you're saying what's the probability of an event occurring once in, say, 50-year time period or 100-year time period. You can choose whatever time period you want, and what it does is it effectively compounds that probability, but it looks at what the probability of the event occurring once in that time period. So that allows you to think about what's the probability that something might happen in my lifetime or during the lifetime of an asset, or perhaps during a period of a policy decision that might be interesting to you, for example, 10 years after a policy comes in. Payback period is something that's used in infrastructure where there's a balance between how much money you make in investment at the front end and how long it takes for that asset to repay the investment at the front end. Imputed cash flows, when you're talking about infrastructure, you're not receiving an actual cash flow, but you are implying what the value that that asset is being provided to you, and that enables you to calculate the payback period. Loss of design life and time to failure are two concepts that I've developed as part of this research, and I'll talk through in a bit more detail on those. And within that, some of the modelling that we did was able to look at whether the atmospheric signal was amplified or dissipated by the hydrology. So we looked at, you'll be hearing me use those terms, amplify and dissipate, in a moment. So just to give you a little bit of a context about how we as service levels are established, particularly for transportation critical infrastructure. And this is in part to explain why we have such large numbers when we're establishing the service level. So the service level is a threshold that we are saying we want that piece of infrastructure to withstand events of that size. When looking at service levels for infrastructure, obviously you want the transportation network to be working so that that enables that economic activity. You also want the some pieces of your transportation network to be even stronger, because when a disaster occurs, lives will be at risk if you're not able to get into those locations, which is your disaster response. And then thirdly, in some cases, there's some pieces of infrastructure you're going to want them to be particularly strong, because recovery becomes much more expensive. Rebuilding becomes much more expensive if you don't have road transportation in. If you're having to ship product in helicopters, there's only so much recovery you're going to be able to do in the short term. So those are some of the key reasons why when we're establishing critical infrastructure to withstand natural hazards like, for example, large volumes of water, you may have quite high standards of service levels for particular assets that are identified as critical. Then what you're wanting to do is figure out how do you estimate what those design specifications would be. And so this is something that hydrologists would do. So my colleague, Christian Zammit, worked very closely with me in developing the model that you'll be seeing one of the results from here today. And just as a general view, if you're wanting to get an understanding about what the design specifications are, if you're wanting to get an understanding of a return period, you effectively need to have twice the amount of records. So if you're wanting to get a 1 in 100 year return period, you need to have 200 years of records. So what that means is if you're looking at a piece of infrastructure that has a return period of, say, 1 in 1,000, you're simply not going to have historical records long enough to be able to do that. It means that you're always a little bit handicapped when you're trying to establish the service levels for critical infrastructure. The other piece is our climate is changing, and the more critical the piece of infrastructure, the less reliable the past climate is going to be. If you think about it, for example, if you're wanting to build a culvert and it's got a return period of, say, a small culvert, a return period of 1 in 5, you can just look at the last 10 years worth of data and you're pretty confident that that's going to reflect what the climate that asset is being built in. But if you're relying on information that's 100 years old, even within those observations, the climate has changed. And then finally, the rate of change in the extremes, just the way the probabilities work, the rate of change in the extremes is faster than elsewhere. So what that means is it's quite difficult to get an understanding of what critical infrastructure service levels will be looking just at historical records. This is to give you an indication, just to give you some context about what are the service levels of particular bridges defined by Whakakotahi. So there's some assets where the return period that the asset needs to be serviceable for and ultimately withstand, and that can range from a 1 in 250 year return period at a 1 in 2,500 year return period. And there's a number of factors that will come into that. Generally speaking, if it's going to be critical for response, if it's leading up to a hospital, for example, you're going to have a much higher service level than you might otherwise. Now I'm going to talk about the loss of design life. So this is the concept that I've developed. To give you some context, I want to talk about probability of exceedance of some particular assets that we have. So if you think about the return period of a 1 in 2,500 year event, so this is something you might have for a hospital, 2,500 seems excessive. That feels like, well, that hospital is going to be standing for a very, very long time. What that means, though, is that when you look at that probability exceedance, what is the probability of that hospital being hit by an earthquake, for example, of sufficient size to cause structural damage? And if a hospital is built to a standard of 1 in 2,500, then the probability over, say, a 50-year time period of that hospital experiencing an earthquake of sufficient scale to cause structural damage is 2%. So it's still quite a material percent when you look at that longer time frame. Our houses in Aotearoa are built to withstand an earthquake of 475 years. That may seem like a weird number to have because it's not a round number. The reason for that is that when you compound that over a 50-year period, which is the design life of houses in New Zealand, New Zealand houses are required in our building code to withstand for 50 years. 475 years average recurrence interval, probability exceedance over 50 years is 10%. So that's the standard that we apply for houses. Just to kind of provide another example, if you live in a floodplain with a 1% annual exceedance probability, or you live next to a stop bank with a 1% AEP annual exceedance probability, over the 50 years time periods of your house, for example, that equates to a 40% probability of experiencing a significant flood. So if you're in a 1 in 100 year flood zone, it's not that there's going to be 100 years before the next event. If you're in that location for 50 years, there's a 40% probability that you will experience that size flood. You'll see on the graph, I've also included the examples of what that would mean in terms of a mortgage, so a 30-year mortgage. So if you have a 30-year mortgage, you're in a 1 in 100 year flood zone, then during a 30-year mortgage, you've got a 27% probability of being flooded. That's why we have insurance. That's why you have insurance even if you're on the other side of a stop bank. Because our stop banks, if they're built to a 1 in 100, they still have a reasonable probability of occurring during having overtopping during the period of the mortgage. So what we did is we developed, so Christian Zammit and I developed an atmospheric hydrological modelling chain, which enabled us to get a much larger data set to enable us to look at what the change in the probability would be under climate change. So we ran this model thousands of times across several river catchments in Aotearoa. What you're seeing here is one catchment. If we've got any hydrologists from Southland, you'll probably recognise your river by the volumes, but everybody else, that just looks like numbers. So what we did is we ran the model in a current state, which is a 1 degree world, and a 2 degree world. Generally speaking, What we found in the catchments we were looking at and other studies done previously suggests that the discharge volume, so the amount of water coming down a river catchment, is represented by a Gumbel distribution. In the work that we did notice that there were some interesting things happening as we went further out, where the distribution seems to be switching from one type to another. That's an area for further scientific investigation. But what we did is we were able to draw the distributions from both a 1 degree world and a 2 degree world, and that then allowed us to estimate how the change in the probability was occurring each year. Now, in order to look at the return periods for a bridge, you're right at that far tail of the curve, so where you see the dotted line. And so what we did is we created synthetic curves based on those two anchor points of the past and future climate to then be able to generate the change in probability on an annual basis at particular locations. So what that means is we were then able to see how that probability of exceedance is changing under a future climate. So the grey line is what you would expect to see in this particular example in a stable climate, and the red line is what that change in the exceedance probability is in a future climate. And what you'll see there is the concept that I developed was looking at this loss of design life as if you have a service level that says you need to have a certain probability of exceedance, and that is changing, at what point do you reach that probability of exceedance in the new climate that you would have only reached at the end of the design life of the asset? So that's that dotted line, the difference between A and C. We modelled a number of different locations. Today I'm going to show you one example of a township in Tokomaru Bay. So it's a bridge, it's the second bridge on the list there. We modelled the entire catchment and to look at the discharge arriving at that bridge. This bridge in particular is part of Waka Kotahi's current end-of-life bridges budget allocation. And so they are currently repairing, reinforcing this bridge to be able to extend the life of that bridge based on the engineering specifications and the expectations about when that bridge may stop providing the service to those communities. That doesn't yet involve climate modelling, but so what I'm going to talk about is how you might incorporate climate modelling into that reinforcement or redesign of the bridge. So here I've got data from Tokomaru Bay. And what you'll see is you've got that shift in the distribution, shift in the probability of exceedance between the current climate and the future climate. I'm also going to show you the difference between if you were to just look at precipitation and not look at hydrology. So what we did, because we built a modelling chain, we coupled the atmospheric model, so that's how much water is falling out of the sky, with a hydrological model which said what happens to the water once it hits the ground. Almost all assessments to date just look at precipitation. They just say how much is precipitation changing. But what I'm going to show you here is how much in this particular situation that would underestimate the rate of change. So this is the difference in terms of the probability of exceedance in terms of precipitation. And this is the change in the probability when you look at discharge at this particular location. So what that means is in this case, and this in many cases, the hydrology is amplifying the climate signal. The change in the probability is greater because of the particular hydrology of that location. So that distance between the probability that you would expect at, say, at the end of 50 years versus what it will be in the future climate is a time to design failure. So how much is the asset life effectively being shortened because of this change in the hazard that it's been exposed to? So the distance is the time to failure, and then the gap between the loss of design life and the original design life is the loss of design life. So What that means is these are some data from our modelling outputs. So it talks about a 1% AEP bridge. So in this case, Circle Base, it's a 1 in 1,000 year event service level. So precipitation would reduce that to 590, but the discharge, so once you add that to the hydrology, that probability effectively halves by 2050. So the probability of a 1 in 1,000 effectively halves. What that means is you effectively end up with a loss of design life under discharge of 19 years, whereas if you were just looking at precipitation, it would be 14. Now, this is design life, so it's not that the bridge necessarily falls over, it's just that it's effectively now significantly below the demands that have been placed on it. And then on the right-hand side, you'll see the estimates with various weighted average cost of capital calculations. So Waka Kotahi normally recommends that you have 4, but they stress test it by 3 and 6 for a discount rate. And so what you'll see there is, given that loss of design life, you're looking at a 12% loss of value for that asset from precipitation, but it's 18% once you take into account the hydrology. Now, this is one example. We did a number of different river catchments, and we looked at a number of different impacts on particular bridges as a result. And just to give you some context, I learnt in the process of this that we've got a lot of old bridges. So from what I can see, there seems to quite understandably been a significant burst of economic activity around the Great Depression. So there are 39 bridges on our state highways that are over 100 years old. There's 260 that are coming up to 100 years old soon. And then there's almost 900 that are 80 years and old. So just to return to what we talked about earlier, those are bridges that were built to different service levels. So before we had a really sophisticated understanding of the sorts of service levels we would expect to see. In some cases, they were built before we even had things like probability of exceedance were developed as a concept. They were built, with different service levels. They were built under a climate that has changed significantly, and they were built where there was very short records about what the sort of water that would be coming down those rivers. So I would expect that, first of all, there is a significant body of infrastructure that needs to be assessed and potentially reinforced. And given the stresses that that infrastructure is going to face, we should expect to see significant numbers of failures across the network as our climate becomes more demanding. So that's my discussion about infrastructure. Now I'm going to talk about what would happen if a public insurer was to step in when private insurers do retreat. So I'm just going to recap a little bit here about the work that I did on insurance retreat, and then I'm going to show what the expectation of payout would need to be given the changing probabilities, these changing probabilities of exceedance under climate change. So just as a reminder how an insurance premium is calculated for a particular hazard. So you have the annual exceedance probability. So that's the probability of a hazard occurring of a particular size. If that hazard of that particular size occurs, how much damage does it cause? So for example, if you have 30 centimetres of water in your house, how much damage would that cause on average? And then you multiply that by the replacement value. That gives you the annual expected losses, which is the core of the premium for that hazard. So what that means is if your replacement costs go up, for example, if construction costs go up, then your expected losses will go up. If your properties for some reason become more vulnerable and a given amount of water causes more damage, then that damage function may change. But the thing that I'm going to be talking about is that if you have a change in the annual exceedance probability, if the hazard, that same size hazard, becomes more frequent, then you should expect the annual expected losses to go up. I just want to do a shout out here to work that was done by the Parliamentary Commissioner for the Environment and a colleague of ours at Steph Gray at the Reserve Bank, but he did this when he was at the Parliamentary Commissioner for the Environment, where they commissioned work to understand how those probabilities would change under sea level rise. And what you'll see here is that with just 10 centimetres of sea level rise, you have a very significant change in the probability of the return period. So in Wellington, for example, with just 10 centimetres of sea level rise, you have a change in return period by 5 times effectively. It goes from 1 in a 100-year return period to a 1 in 20-year return period. Auckland is a bit slower. The reason for that is not that sea level rise is any different between Auckland and Wellington. These are exactly the same amounts of sea level rise. The difference is primarily because of the tidal range. If you have a small tidal range, then the probability of a storm surge coming in and overtopping is greater because you have this tidal range is less able to absorb the storm surge. Whereas in Auckland, for example, with a large tidal range, you've got a better chance of that storm surge occurring, storm surge occurring at low tide. If it occurs in low tide and you've got a large tidal range, then it just gets absorbed within the tidal range and nobody notices. So this is work that I published with Sally Owen, Alan Noy, Christian Zammit and myself on Insurance Retreat. Sally Owen did some fantastic work on the GIS and modelling what the impact would be for a damage function on a house-by-house basis. So this talks about the insurance retreat that you would expect to see at the coasts. And you'll see that you've got partial retreat. So partial retreat is where an insurer transfers some of the risk back to the homeowner. And whereas full retreat is we anticipate when insurers stop offering insurance. Now, I want to point out these thresholds here. So I'm looking at a 5% annual exceedance probability threshold for full retreat and a 2% threshold for partial retreat. These were estimations that we made. There's subsequently been work done, particularly in Australia, looking at affordability thresholds. And so I'm going to talk a little bit about what that might be in terms of affordability thresholds. So to give you just a couple of examples, taking that calculation, to give you some examples of what that would mean in terms of the insurance premium as the annual exceedance, annual recurrence interval changes. So if you had a $500,000 house, now this is the building, not the land, a $500,000 house, and you had a storm surge that was of sufficient height to cause 30% damage for your property, then a 1 in a 100-year storm of that size, the premium you would expect to pay just for that hazard without any loading from the insurer in terms of their capital reserves or their profitability or their administrative costs, the premium you would expect to pay for that 1 in a 100-year storm surge would be about $1,500. As that probability changes, however, it has a direct translation in terms of the premium you would expect to pay. So we used a threshold of 1 in 20, which is approximately 5%. The reason it's 4.88% is just it's just the way the calculation works. You recall I mentioned earlier that if you are above 100 years, you can just go 1 over 100. But if you're less than 1 in 100 years, you have to use the log. So there's a formula there if you want to have a look at that. I can show that later. But what that means is that with a 1 in 20 years, you're looking at an insurance premium just for that hazard, so not wildfire, not for earthquakes, of over $7,000. Some work that's been done in Australia is looking at affordability thresholds and looking at measures such as 4 weeks disposable income or 4 weeks gross income. If you were to look at 4 weeks of gross income, if you look at median income and medium house values outside of Auckland, for example, then you might be looking at an annual exceedance probability of about 3%. So work that Australia is doing, if you translate those very roughly into New Zealand numbers, that works out at a affordability threshold of 3%. So what that means is the threshold that we've previously used when looking at coastal inundation and coastal insurance retreat at the coasts is conservative because it's 5%. To give you a point of comparison, in the UK, when the threshold that private insurers used when they were indicating that they were going to withdraw covering for floods in the UK was a 1 in 75 years. So that's 1.32%. So well before the thresholds that I'll be talking about. And then just to give you, to kind of play this through, you will recall that slide that I showed previously from the Parliamentary Commissioner for the Environment. What it indicated is that with 30 centimetres of sea level rise, a 1 in 100-year event will become a 1 in 1 year event. What that equates to is a $95,000 premium. So I say this because if we are looking to extend public insurance where private insurers have pulled out, the effective subsidy of providing cover for that hazard is with 30 centimetres of sea level rise would be approximately 95,000, and that's not the maximum. It would keep going up because the water keeps turning up. When we first published the work on insurance retreat, we did briefings for a number of organisations, and the overwhelming, most common response that we received was, well, we don't really need to worry about this. Won't EQC pick it up? EQC at the time is now the Natural Hazards Commission. And we contacted Natural Hazards Commission at the time, said, by the way, everyone thinks you're picking this up. That has only reinforced since then. So there's lots of discussion in the public about, well, shouldn't the Natural Hazards pick this up? And I wanted to point out a few key differences between natural hazards, between the seismic risk that natural hazards have very effectively provided for Aotearoa and why extreme weather hazards are much less similar to what they've done in earthquakes. So first of all, the probability of seismic hazards is not changing. We're learning more about it, but they're not changing. So a 1 in 1,000-year earthquake is still going to be a 1 in 1,000-year earthquake in 100 years' time. Whereas, as I've shown previously, the probabilities of the extreme weather events are changing. They're escalating under climate change, and the rate of change is accelerating. A second piece is that in part because of this, but the reinsurer's appetite for providing cover to Aotearoa is strong, whereas the appetite for providing cover on extreme weather is weak. Part of that is because the probabilities are changing, but part of it is also our country is very attractive to reinsurers because we are uncorrelated to other risks when it comes to earthquakes. But when it comes to extreme weather, there is some correlation from a climate change perspective, and there's also some correlation in that some tropical cyclones can hit Australia and then travel down here as well. The other key thing is that seismic risks, the probabilities tend to be very low, whereas the probabilities of extreme weather are low, but not very low. For example, there's still work being undertaken to estimate what the return period of the Canterbury earthquakes were. There's some numbers ranging from 2,000 return period to a 10,000-year return period. Whereas if you think about Cyclone Gabriel, for example, that's about a 30-year time period for an event of that size. The return period for a major event that we're most confident on is the Alpine Fault, and that has a return period of about 1 in 300. So even compared to that, when you compare that to Cyclone Gabriel, the return period is much greater. Now, the Alpine Fault will cause more damage than Cyclone Gabriel, but it just gives you an indication that when the reinsurers are thinking about what they're interested in, the very low probability of seismic makes it attractive. And then the other key thing, which is makes the difference between seismic and extreme weather, is that within a region, so if you're in Auckland, which particular house gets hit is largely random, unless you're actually on a fault line and that fault line goes again. Then which house in particular is going to get impacted is random. Whereas when it comes to particularly water flows downhill. And to quote a favourite quote of someone at Auckland Council, he commented when his councillors asked him, where is the problem? And he said, it's at the bottom of the hill. And they said, which hill? And he said, every hill. So basically, when it comes in particular to coastal inundation and flooding, the lower your house is, the more water that is going to turn up, the greater the damage. And because you're at the bottom of the bowl, smaller events are more likely to impact you, which means you're also more likely to get hit with greater frequency. So from my perspective, there are key differences between seismic risks and extreme weather risks when thinking about whether a public insurer should step in. So to give you some numbers, what I'm going to show you here is that probability of exceedance curve. And what I've done here is I've made some assumptions about when private insurance might retreat. Now I'm going to provide some information on coastal inundation, and I'm going to do a comparison for flooding. Coastal inundation, I'm going to talk about a 1% AEP coastal inundation zone. When I'm talking about flooding, I'm going to talk about a 2% AEP flood zone, which is basically a 1 in 50 year. I didn't do the 1 in 50 or for the coastal, is that I don't know how those houses have still got insurance to begin with. So, but if we look at coastal inundation, if we were to apply the threshold that I discussed previously of a 5% threshold for insurance retreat, or 4.88% to be precise. Now you'll see a single point on this curve. Obviously there's some uncertainties here, but for the purposes of illustrating this, I've chosen a point within the modelling. So if you were to look at a location, for example, in some of the coastal inundation zones in Wellington, you would expect to see insurance retreat in 2040. And so what I've done here is said, if you had insurance retreat and a public insurer was to step in, what is the probability of that public insurer would have to pay out over the remainder of the century? And what would they need to pay out in the first 10 years? So in this particular location, in a coastal inundation zone, a 1% AEP in Wellington, you're looking at a 54% probability that the public insurer would pay out within the first 10 years. And for the remainder of the century, it's 100% probability. Now, it goes to 100%. This only shows a probability of an event occurring once. Obviously, in these locations, you would have multiple, but the probability exceedance method just talks about an event occurring once. The grey line is what that would be if it was a stable climate. If that 1 in 100 year event remained a 1 in 100 year event, it didn't change, in which case you would have a change and you would have a payout within the first 10 years of 9.5%. So what if insurance was to retreat sooner than that threshold I applied? So what if it was to retreat within a 3% threshold? So it would occur earlier, and there would be you would have about a 34% probability of being paid out in the first 10 years. The reason that there's difference is that the rate of change is accelerating the further out you go. When you're looking at inland flooding, you remember I mentioned earlier that the rate of change is slower. So if you look at inland flooding, you may not have insurance retreat until well later into the century if you apply that 5% probability. So again, you'll see here that 10 years after a public insurer was to step in, you'd have a 41% probability of paying out. If that threshold was sooner, though, you had an affordability threshold, for example, of say 3%, then you'd be looking at insurance retreat in the 2040s, and you'd have a 29% probability of paying out in the first first 10 years, and then a 94% probability paying out for the remainder of the century. Then I'm going to compare that very briefly to what that might mean in terms of earthquake risk. So what does that mean, for example, if we think about the Alpine Fault? So the Alpine Fault's got a return period of approximately 1 in 300 years, in which case, and that is something that EQC obviously already covers because it's a seismic risk. So the probability of, with an event of a 1 in 300 year return period, you're looking at about a 3.3% probability paying out within the first 10 years, whereas from a weather perspective, you would be paying out 25% of the time. So this is assuming you had an insurance retreat occur on a time, not to do with a particular threshold, which is 2035. We did recently some work with the Ministry for the Environment to try and get an understanding of the number of houses that are would be exposed to significant damage. And so what we looked at is some different thresholds. One of them was a 20% damage, a 50% damage, and an 80% damage. We looked at, just to give you a translation, that's 30, so 20% damage function means relates to 30 centimetres of flood water coming in above your ground floor, whereas a 50% damage function assumes 1.2 metres of flood water and 80% is 3 metres. Now, bear in mind that when you have that 30 centimetres, that's not clean water. That tends to be water that is heavily polluted, which is partly why just a relatively small amount of water can cause significant damage. And so some of the numbers that we put together for the report, we were asked to look at the number of houses that could expect to experience damage in the next 35 years. But what embedded within that is the number of houses that are exposed to significant damage inside our floodplains. And so what you're looking at is about 4,000 houses that are exposed to significant damage. And here we use that threshold of the 20% damage threshold, so 30 centimetres of more of water coming in. Whereas in inland flooding, you're looking at 46,000 houses and the relative property value between the two. So this gives you some indication. This isn't these are houses exposed to a certain amount of water. We don't have currently publicly available information of the number of houses that are exposed to a 1 in 50 year flood zone that may be coming available. There is a major project that's finishing in the next couple of months. But that gives you some context of the amount of houses involved if you were to be looking to provide public insurance. So that is the key findings of 7 years of research in some cases. So look forward to your questions.
Kia ora, Belinda. Look, that's all fascinating and I think really eye-opening for many people to actually see some of those figures pulled together. We are getting quite a lot of questions through, so I'm also going to encourage people, you have some power to vote as well, so feel free to kind of like particular things if you want to make sure they rise to the top of my list as I work through some of the questions to pose to Belinda. And also, I guess, just conscious that there's a couple of sections here, as Belinda noted at the beginning, and so there might be some questions that are in the infrastructure space and design life and design specifications, and some in the public insurance space too. So actually, what I'm going to do is I'm actually going to start with some just in the infrastructure space. There's a kind of a question from Kushla about whether you can explain in a bit more detail between sort of loss in service and loss of design life, and are they the same? I'm also going to kind of just tie into that bit of a question I had as we think about loss of design life. I'm conscious that the marginal cost of building in resilience when you're actually developing the infrastructure can be a lot less than it is when you actually have to replace it in design life. So are there any kind of things around how we think about how you can build into that concept of loss of design life where you are looking to build in more resilience, or how we can understand what that might mean in terms of design specifications.
So definitely the same methodology can be used to calculate how much stronger would you need to build it today in order that it maintained that probability exceedance service level throughout the life of it. And what that does is it also means that you're not overbuilding. So if you were to attempt to build for a 2-degree world, for example, today, you may actually overbuild in a sense because there is that change in the probability over time. So yes, it is absolutely something you could use to calculate if you wanted to have the probability exceedance service level equivalent to a 1 in 1,000 years over the length of the asset. How much stronger might you need to make it today, like 1 in 1,200, to make sure that it met that service level over time? So yes, it can definitely be used to estimate. Now, bear in mind, these estimates are looking at a national scale. They're not replacing engineering assessments. You would always do an engineering assessment at a specific location. But what this indicates is it's a methodology that would enable us to get an estimate of the entire portfolio for the country, and that we would be able to estimate how much stronger we would need to make those assets. Kushla, thanks for your question. So on your question, what we do is I'm very happy to have a conversation with you afterwards, but we hold the service level constant, and then we say, given that service level is something that society is expecting for this particular location, at what point will it start to not meet that standard level, and approximately how many years are shaved off the design life? So we hold the service level constant, and then we adjust the design life compared to the time to design failure relative to that design life. What Vicky's just asked about is that you would hold the design life constant and you would change the service level. So yes, that's definitely something we can do.
Just kind of continuing off the theme in the infrastructure space as well, Mela asked, do we know how much protective measures such as flood barriers reduce the impact on properties, and is it worth it? How do we know when it's worth it?
So there is, we don't have a comprehensive publicly available inventory of those defences. So it's very difficult to get an estimate of what that analysis is. Generally, what we find is that when you build a stock bank, it does provide a sense of security. People describe them as protections. I call them defences because I think the protection term gives a false sense of security. It doesn't reduce risk, it suppresses moderate frequency risk. So if you build a stock bank for a 1 in 100 year event, it will hold back the 1 in 100 year event, but it doesn't hold back the 1 in 200 year event. And so what you have is something that's called the levy effect, that when you build a stock bank, people build more assets behind that stock bank because it feels more secure. But actually you can increase the risk to life if you build a stock bank. Because what is a stock bank? It's effectively a long, skinny dam. And what happens is when a very significant event comes through, that dam can break. And so, for example, some of the fatalities that occurred during Cyclone Gabriel were in part because the water turned up so fast. If there hadn't been the degree of stock banks there, then you would have had the water turning up slower and you would have been more able to evacuate.
Which also comes back to that differentiation you had in between where it was precipitation and where you took into account the hydrological impacts. Jeff has asked whether the hydrological model could look at other physical characteristics. So he gives the example of could you be able to identify what the impact of permanent afforestation in the upper catchment above Tokomaru Bay could be in terms of that loss of design life?
Yes. So that is something we can do. So one of the things you can do is you can say, what would the flow of water be if you had the what is currently pasture upstream of that location was replaced with native forests versus exotic forests, you can run that model in to see what that does to the change in the probability. Yes.
Thank you.
Just to add to that, we have used this model to look at what the impact on flooding would be from restoration of wetlands working with Ngāi Tahu. So we've done that in the South Island, looking at how much restoration of wetlands in various catchments in the Canterbury would reduce flood risk coming down.
Thanks. And I might just keep with one more on the hydrological point, which is it's just a question whether you can explain for a layperson what the intuition is behind how hydrological factors creating discharge beyond what precipitation alone would create.
So a key piece, when you have a situation where the atmospheric signal is dissipated, you might, for example, have a very wide and broad catchment where the water is falling down and then spreading out, in which case you may have a lot of water fall down, but it actually has quite a wide area for it to drain from. If, on the other hand, you had a very narrow catchment with lots of hills to catch that rain, so you had a certain amount of rain come in, it had the orographic effect where it hit the hills and then it falls down, and then it's concentrated into a very narrow area of space, then that signal may be stronger. So that's situations where a 7% change in the precipitation, which you would expect to see with 1 degree of global warming, might result in more than 7% increase in the discharge.
Thanks. I'm going to pick up on a couple of questions where people are making some of the kind of comparisons between the seismic risks and the water-related risks, be they sea level rise or be they, I guess, inland hydrological as well. So there's one question from Rob, which says how you might consider where there may be, I guess, intersections between seismic risks where they might be exacerbated by climate. So could it, a tsunami or sea level rise, may that impact liquefaction risk, and then how that may be considered by insurers if they're thinking about an intersection of risks. The other one, James asked a very local question, is the Wellington Council's focus on making buildings earthquake proof somewhat misguided, looking at your probabilities of earthquakes compared to severe weather events, and actually should there be greater focus on hydrological resilience, and what might that entail?
Okay.
So different, but into kind of setting.
So yes, absolutely. So while climate change does not cause tsunamis, it does lift the base on which those tsunamis arrive. So if you have, say, 50 centimetres of sea level rise, and then you have a 50 centimetre tsunami come through, that's the equivalent of what a 1 metre tsunami would have been in the past. So sea level rise lifts the base of tsunamis. So yes, it definitely does change the reach of those tsunamis, even though it has no causal effect on the origination of the tsunami itself. And the same thing with liquefaction. So if you have locations that are simply just, first of all, from sea level rise, you have sea level rise coming into particular locations, or you have locations that have much more frequency of being completely sodden, and then you happen to have an earthquake occur during that time. So yes, liquefaction can be a seismic risk that is exacerbated by either sea level rise or sheer frequency of saturated soils. When it comes to the earthquake piece around Wellington, there's a couple of things to bear in mind. There is our standards that we have for buildings for risk to life, and then there's the standard that an insurer might apply about whether they want to insure your property or not. They're different. You can have a house that meets the building code and is not insurable. So the standards that we have for earthquakes, particularly in Wellington, are very much driven by risk to life. as a society, we measure what we, that is something that we measure intensely and value greatly. And so the thresholds that they're applying to earthquakes and here are predominantly related to risk to life. As I mentioned earlier, in Aotearoa, because we don't have a significant wildfire risk, most of the cases that we have with regard to extreme weather events related to storm surges and flooding are things that you can evacuate from. So the risk to life is manageable, as long as you don't keep building really long, skinny dams next to people, in which case you do have a change in the risk to life. But the focus in Wellington is very much around that risk to life.
It's a helpful clarification about why you say that, why that emphasis plays out. There are lots and lots of other questions coming through, so I'm just going to pick another one that is getting a few votes at the moment. And I think it'll be interesting to just kind of touch on some of the, start to touch on some of the issues around insurance as well that that you're picking up there. Also conscious of, you know, the theme of this is around fiscal too. So you talked a bit about the limitations on data and asset exposure just before. Be interesting to know where you see any key gaps might be and how that might be further developed. I guess what I'm also interested in that context is the sort of sense of awareness of some of these numbers and some of the kind of potential impacts. Just also related, I'll pick up another question from Alison in this little group, which is, have you thought at all about the likely future effect of loss of insurance or affordability challenges around insurance on property values, which is obviously always a very interesting topic for New Zealanders.
So we have, where do I start on data?
Sorry.
We have a significant investment in the past in understanding seismic risk for very good reason. We are late to have the same degree of investment in understanding extreme weather events. So Alan Noy and I and Dave Frame were part of a research program that looked at a 5-year research program modelling extreme events funded by MB. So, and that was the first major event, program of its kind. So we have tended to not invest as much money in looking at extreme events. That said, overall, we have, there is a bigger gap when it comes to data, and that is accessibility. So even the data that we do have, it is not accessible. It is not accessible to the public. It's not accessible to most researchers, and it's not accessible to small to medium businesses. Information is available because from the Earth Science Institute if you have enough money. So if data is available if you have enough money, and the entities that tend to have the money to pay for that would be the insurers and some of the banks. But we have a significant issue with data accessibility, not just the quality of the data. So while there could be more investments in research with regard to extreme events, we predominantly an immediate need is to make that data accessible. And then adding to that, while we have a good understanding, we have made investments in hazard, and we've made some reasonable investments, and so that's what is happening to our climate. We've made some investments, lots of investments in understanding our exposure. We haven't made nearly as many investments in understanding our vulnerability. So whether that's the vulnerability of individuals or vulnerability in terms of economic costs. So we have underinvested in understanding what the economic costs of this are. So there is a significant opportunity from a data perspective of making existing data more available and getting a much better understanding about vulnerability and continuing to invest in climate science. I just wanted to touch on one piece of there about there is some information that has been publicly available. So the Natural Hazards Commission is doing excellent work in making information available with a public portal, so making that information directly available. The only thing to bear in mind is that it is heavily weighted towards earthquake risks, just because that's what NHC does. It's based on claims. NHC, while you do have some claims for NHC for storms, they're only for the land, so you'll tend to see extreme events very underrepresented in that portal just because of the nature of the requirements of NHC. Now, looking at property values in hazardous locations need to come down. They are overvalued. They are not reflecting their climate risk. That is balanced by the fact that we have had such significant values in the last 10 years. So I would argue that many of these locations that are going to lose insurance are probably overvalued by 30 to 40%. I have my climate leases model has a mechanism to quantify that, but as a rough rule, they're probably overvalued by 30 to 40%. Which is less than the amount of appreciation in property values that we've had in recent times. So effectively, property values in most hazardous locations need to go back to where they were 10 or 20 years ago. They are overvalued. If we continue to prop them up by providing a public subsidy, whether that's the state being the insurer of last resort, so effectively stepping in when there is a major event, or we provide a different form of a subsidy where we provide an uncapped, unending subsidy from a public insurer stepping in, those property values will continue to be mispriced.
I agree with what you say. I'm going to come to one technical question from Anna, and then I'm keen to come back a bit more to the sort of public insurance and the I guess the fiscal piece of it. Anna asks, what's the current criteria that insurers apply or rely on when assessing risk due to natural hazards? Do they rely on current information, for example, that's contained in a limb on a property or in a district plan map, or are they relying on other information?
It's not, I'll give a very general response here. I mean, each one will have their own view. You are best to ask an insurer, but they'll have their own view. Some of it will be based on the claims that they've previously had, so the data that they hold. They have been moved by insurers in recent years to increase their understanding of natural hazards. Sometimes that's driven by their reinsurers, where their reinsurers say, we want you to have a better understanding of that. So it'll depend. In most cases, they're not going, by the time information ends up on a limb, the insurers have probably already formed a view of it. So there is this perception that if information is made available, then the insurers are going to act. The insurers may act when the information becomes available, but not because they didn't know it. It just provides them cover for them to act on it. So providing markets work better with better information. Insurers are making these assessments internally. They're not going to be, they're less likely to be directly impacted by an information that ends up on a limb, because they will most likely to have already made an assessment. One thing to keep in mind, though, when you're thinking about the horizon of an insurer, because insurance policies are only for 12 months at a time, an insurer doesn't need to be thinking about 5 years from now. They do not need to be thinking 20 years from now. So while insurers are making assessments, they have only a modest appetite for thinking about future modelling, because that's simply not their business.
That's really useful to hear as well, Belinda. I mean, certainly my impression from insurers is actually they often have far more precise property by property information about likelihood to flooding, for example, than people probably appreciate. And so, but also what I've learned is that some of them are also quite willing to consider how mechanisms that will make an individual property more resilient, how that might impact on premiums. I know I've spoken to someone who, this is not possible obviously with a lot of properties, but who has actually lifted their house by a metre and seen a benefit for them in terms of their insurance premium. So, yeah.
Yeah, in New Zealand, because our floodplains tend to be wide and shallow, and our floods tend to not be particularly deep, what that means is that if you can lift your first floor height sufficiently high, then the amount of damage your property will experience is quite modest, or you may not experience any damage at all. Now, that doesn't take into account landslides. That's a completely different hazard. And I haven't talked about landslides today because we don't really have an understanding of how those rates of change are changing. But landslides is a significant risk. The good news is landslides are covered by EQC, by NHC.
So I just wanted to touch on a little bit more the differences that you set out between that flood risk and that seismic risk, and how you might think about the public policy case for whether to consider public insurance or not, or when, in terms of flood. I mean, one of the key things, I guess, I would take from the fact that you have NHC is you would effectively, if you were applying it to flood, as you talked about, it's a subsidy. Effectively, what you're also doing is you are imposing an additional cost on people who are living in less vulnerable areas. And so you get more of a muting of the sort of signal between where the incentives might fall on individuals to actually respond to the risk that relates to their property or to manage it where they can. Which might therefore mean that you actually have people stay in riskier areas for longer than might otherwise be the case. Whereas as you kind of set out with a more random distribution on the seismic, you don't have that sort of subsidy playing out in quite the same way. I don't have a kind of specific question there, but I just wondered if you wanted to comment on that any further.
Yes, so one thing I would say is that you will have picked up my concerns about a public insurer stepping in, but I've been convinced by colleagues, particularly Ilan Noy, that a public insurer may be inevitable in some circumstances. But what I would say is that if public insurance was to be extended, it must come with a requirement that if damage of a certain threshold is reached, you must move. We cannot have an unending public insurance being offered in locations where the probabilities are changing so fast. So there may be a role for a public insurer, but it must come with a requirement that if a damage of a certain threshold is reached, then the house is not rebuilt. Or you'll sometimes hear people say things like, we shouldn't be building in dumb places. I would add to that and say we shouldn't be rebuilding in dangerous places. Once an event occurs of a sufficient size, then we should have mechanisms to move people. And having an uncapped, unending reinsurance, public insurer will result in people remaining in hazardous locations for indefinitely. That has happened overseas. It's a policy failure overseas in a number of different situations. And then the other one, picking up on your point about affordability, we are already reaching points where insurance is becoming an affordability issue in particular regions. Following, for example, Cyclone Gabrielle, you're hitting, in some cases, insurance premiums, the median insurance premiums hitting $2,000-3,000. That starts taking up a significant chunk of median income in those regions. The danger is if we don't move to risk-based pricing, if we don't consider moving people out of these locations, you may have that subsidization causing affordability issues in locations outside the flood zone and having people there dropping insurance from a portability perspective, even though they're exposed to earthquakes and fires and all of the other hazards as well. So if we require this cross-subsidization to continue, and you have this escalating hazard in the most most hazardous locations, then you may end up pushing affordability for everybody, not those people in the hazardous locations.
I'm going to slightly adapt Alexi's question on insurance retreat as well, and then I'll make sure we have time to move on to the others, which is, do you think that we will see a kind of measured erosion in insurance accessibility or provision, or will we see a collapse in that in terms of insurance retreat happening quite suddenly, quite quickly? And I'm adapting Alexi's question because Alexi's question is also about, do you think the property prices will see a kind of rapid shift, or will that potentially erode more slowly over time?
So insurance retreat, the time frames for properties that are most exposed to coastal inundation are getting fairly close. It's possible that insurers wait until the threshold that I've talked about, but insurers could very easily move sooner than that. They may move sooner because they reassess that. So they might, for example, look at that threshold that was applied in floodry, that led to floodry in the UK. So they may apply a threshold where they don't wait until it gets to 5%. They're moving much sooner, perhaps a 2 or 1.5%. The other thing is insurers will respond to what reinsurers are doing, and reinsurers may stop providing cover in particular hazards, not in response to anything happens here, but something that happens in other countries. So they may, if there was a series of significant hurricanes to hit, for example, that hit major metropolitan areas, they may say, we're not going to cover that storm surge at all. And so there may be situations where insurers act sooner than that. So it's unknown. It very much depends on that particular market. What that means for property prices, when insurance becomes unavailable, there will be a shift in property prices because it will be very difficult to borrow. You can't borrow in New Zealand unless you have insurance. The longer we delay in making policy changes, the more likely that that shift will be abrupt. If we were to take a planned approach to thinking about these very difficult questions, you could have a gradual decline in property values, or property values holding steady and not increasing any further in these hazardous locations. Because there is time for some of these properties, but it will depend on what the interventions are. If we prop them up and then there's a reason where that becomes unsustainable, then you will get a sharp adjustment. But if we can make some of these difficult decisions sooner rather than later, you could lead to a smooth adjustment of property prices.
I want to kind of pick up on a couple of questions that are a little bit more thinking about community, not just individuals as well. So Eric has asked a question, I guess, in part around how do you think about how letting residents decide what works, what it might be to be cost effective for a community rather than necessarily just the sort of individual. He specifically says this in terms of, what might be cost effective rather than having endless subsidies or mispricing. There's also a question from Monica thinking about sort of the human societal impacts as well, and how you might think about quantifying the benefits of infrastructure and investment in public assets that I guess takes into account the sort of slightly wider gap between what people and communities might need to be resilient and what would be cost effective. So just any kind of comments from a...
Yeah, So I think at the moment we tend to focus very intensely on those individuals in the hazardous locations, and we're not thinking about what the trade-offs we're making for broader communities. So, for example, there is a significant amount of money being spent on stock banks for defending particular locations, but are we making, and the danger is that those investments may divert funds from other things that might make things more resilient. So if we think, for example, about our roading network, being able to get to school, get to work, attend your family member who may be ill in hospital and the like, those sorts of activities are currently undervalued when thinking about the resilience of our roading network. We're not thinking about that, partly because we haven't studied all of those impacts. There's some analysis undertaken at Waka Kotahi, but we're not looking at what how the frequencies of those events are going to impact those roading networks and what that means for those broader well-being measures that Treasury has taken a leading role about extending just beyond the financial and thinking about the other well-beings. Instead, what we're doing is that I think there's a diversion of resources thinking about, well, we want to hold our line in this particular location and we want public funds to build these defences because people have understandably a strong sense of association with place. I do see that there is an exception with that in terms of those iwi and hapu communities that have a unique attachment to place, and whether the solutions for them may need to be different. But at the moment, in a lot of cases, we're presuming people should be able to stay in these hazardous locations and asking for policy to be designed to enable them to do so, when I would argue the change in the probability is so significant, it's only a matter of time before they're going to have to move. And so we need to be making decisions to smooth that transition.
And that is something that experience suggests that politicians included, are very reluctant to tell people to require people to move. So it was interesting to hear your comment about if there were public insurance, actually, the quid pro quo of that could be that actually, in your opinion, that you should be able to require people to move.
And when I talk about people moving, part of that is allowing the market of these properties to adjust by removing the subsidies. That will discourage people. Sometimes here people will say things to the effect that, which is, I understand, a concern that if property values fall in these hazardous locations, will more vulnerable people end up living there? They're less likely to be first home buyers though, because banks shouldn't be lending on them. Simply because banks are starting to get a much better understanding of that, and also if they haven't got insurance. So they are likely to end up with situations where they have people who are renters, and so we need to think about what that means. Some of the work that Alana has done, though, has shown that when people are renters, if they're able to move out of that place, they're actually less impacted than by homeowners who remain in a hazardous location. So their well-being is more impacted if they're not as mobile.
That's I think important to be able to better understand, because that kind of concern around vulnerable people and what might be the impact if you had property drops in particular areas is definitely something that gets quite a lot of interest and attention. Mm-hmm. Yeah. I am conscious that we are running out of time. So, and I am also conscious that I have deliberately not gone to some of the questions around which RCP has been used. So I just
4.5.
Well, no, so that's been picked up, but there's a sort of question of, well, that's different to what's currently required of local governments. Mm-hmm. And yes, I think therefore that would mean that probably it would suggest that local authorities are being less conservative in how they're thinking about land use. Would that be the
Oh, so
than what this might assume is actually the risks.
Yeah, so just to explain so I use 4.5 because we do have data accessibility constraints, and so I use 4.5. I also look at higher RCPs as well. I can, if asked, I can share that information, but it just gets worse basically. So yeah, it's not that it's not there, it's just my numbers are,
Exactly. Thank you so much. I also, Eric asked a question of Treasury's work, and I think your question, Eric, was probably in thinking about the revenue raising mechanisms around specifically communities. But I did actually just want to specifically say that, coming back to that infrastructure piece, given the Crown owns quite a lot of infrastructure and invests in quite a lot of infrastructure, that is something we are mindful that actually there would be value in us being able to understand that a lot better than we currently do in terms of some of the risks. So that is definitely on Treasury's mind as an area for our work as well. So just kind of pulling back some of the elements of the potential implications for the Crown from a fiscal point of view of both of those parts of your presentation. Look, that has been just fantastic. Really valued your time, Belinda. I think that your work is really important for not just policymakers and decision makers, but actually for the public discourse that I think is going to have to increasingly happen in New Zealand as we think about what is this shift and that kind of dimension of the rate of change that you talked about in terms of this particular hazard. What does it mean for New Zealand and New Zealanders? So just want to really appreciate your presentation today and your time. Thank you everybody for your contributions and your questions, and apologies I haven't got to them all and may not have done some of them justice, but just a big thank you. It's been great having you with us today.
Thanks, option.
Piki te kaha, piki te ora, piki te wairua, huie, ki e. Masiwa.